So, last class I have discussed that how theoretically we can generate load settlement curve for pile, and in that approach we divided the pile into number of segment, and then for each segment we determine or calculate the settlement at the center by assume a tip deformation, and then we will get the PU ultimate load carrying capacity of the pile and the settlement of the pile at the top based on one particular assumed tip deformation. So, now if we changes the tip deformation value, then you will get different PU and delta. So, this way you have to repeat this process by different del yp value, and then you will get the load versus settlement value for different tip deformation. So, under different tip deformation we will get a deformation of the pile top and the load. So, that you have to plot and you will get the load versus deformation curve. Now, next today I will discuss the another approach, which is the elastic analysis. So, based on elastic analysis also we can generate the load deformation curve theoretically. So, elastic analysis is what? In elastic analysis also pile is divided into number of uniformly loaded elements. The solution is obtained by using displacement compatibility between the pile and the adjacent soil. The displacement of the pile is obtained considering the compressibility of the pile under axial load, and the displacement of the soil is obtained by using Mindlin equation for the displacement of soil mass due to loading within the soil. So, if you get the detailed solution procedure of this process, then you can go through this book. I have given the reference. So, this pile foundation analysis and design by Paulus and Davis, you will get the detailed solution procedure. So, I will not discuss that solution procedure. I will discuss how I can apply that approach to determine the load settlement curve. So, detailed solution procedure is available here. So, in this method, so what is that we can determine how much load is transferred to the pile tip when we apply a load on the pile top. So, that value or that expression is given for floating pile . Floating pile means pile is not resting on a rigid strata, it is on a uniform soil, okay, or where for the floating pile the proportion of transferred to the pile tip beta can be expressed as beta 0 C k into C nu. So, what is beta 0? Beta 0 where beta 0 is okay. So, where the beta 0 is equal to beta 0 is equal to the load portion where beta 0 is equal to the tip load portion for incompressible pile. When the Poisson ratio mu is 0.5. So, that means if the pile is incompressible and the soil Poisson ratio is 0.5, then we can use beta is equal to beta 0. But if the pile is not incompressible and the mu is not 0.5, then you have to apply two correction factors. So, those two correction factors are C k and C nu. So, C k is equal to correction factor for pile compressibility. And C nu is the correction factor for Poisson ratio. Of the soil. So, how I will get this beta 0, C k and C nu? So, this beta 0 I will get from this value, this chart. So, this is for L by D, different length by diameter. This is the beta 0 value and this is dB is the diameter of the base. Suppose if uniform diameter, then dB by B will be 1. But if the base has an enlarged diameter compared to the shaft, then we have to calculate dB by D accordingly. Otherwise, if the shaft diameter and the base diameter is same, then this dB by B will be 1. Then C k will get for this chart, and where k is called the pile stiffness factor. Which we can calculate the elastic modulus of the pile and Ra divided by elastic modulus of the soil. Now, for solid pile, Ra is equal to 1. Or for hollow pile, so this is the solid pile, Ra is equal to 1, and for the hollow pile, Ra is equal to pi by 4 d 0 square minus d I square divided by pi by 4 d 0 square. So, for the hollow pile, this will be d 0 square or d outside square by d inside square divided by d outside square. So, diameter of the outer diameter of the pile and is equal to do and inner diameter of the pile is equal to di. So, for the solid pile Ra equal to 1 and for the hollow pile. So, this is equal to the effective area divided by the area covered by outer surface of the pile. So, here effective area is this one, which is the hatch portion, and divided by the cover by the outer surface of the pile, which is d outside square. So, this is the Ra value we will get. So, once that means it is very high, very stiff pile where the stiffness is very high, you can see, then the correction factor is 1. So, that means if the pile is incompressible or very stiff, it will not compress, then the correction factor is 1. And if that means if the soil Poisson ratio is 0.5 and the pile is very steep, then beta will be equal to beta 0. Otherwise, we have to apply this correction. Similarly, for the Poisson ratio also, you can see 0.5 it is 1, otherwise we have to apply these corrections. Okay. So, this is for different k value, and k value I have discussed how to calculate. So, this is for the floating pile. Similarly, for the end bearing pile, on stiffer material or stiffer medium, then the beta is equal to beta 0 C k, then C nu and C b. So, the C k and C nu are same as we have discussed for the floating pile, but say C b is introduced. What is C b? C b is the correction factor for stiffness of bearing strata. Okay, so, how I will get this C b value? So, C b value I will get by using these expression. So, that means here the pile is on the bearing strata or a steep strata, stiffer boundary, where this is the E s and this is the E b, okay, or the base soil where pile is resting. And previous case, the floating pile means this is the pile which is in a uniform soil, and that soil is extended up to a deeper depth. Okay, so, that is for the floating pile, and here it is resting on a stiffer media, okay, or stiffer strata. So, now this is E b by E s for different L by D ratio. This is L by D ratio 75, 50, 25. Then this is 10, this is 5, and this is different k value. K value I have already discussed. Then if I know the E b by E s and the L by D ratio and the k value, then I will get the correction factor. Okay. So, this way I will get the correction factor for different L by D ratio, that is the L by D ratio 75 to 5. So, this way I can calculate that how much portion of the load is transferred to the tip of the pile when we apply a load on the pile. So, that means some portion is taken by the friction, some portion is tip. So, this beta is the portion of the load transferred to the tip. So, if the P is the applied load, then the P p will be equal to beta into P, because that portion of the load is transferred to the tip. Okay. And then the P s, that is the friction, that will be equal to P minus beta P. So, that will be equal to P 1 minus beta. That means, beta is equal to 0. That means, all the stresses are taken by the friction. If beta is equal to 1, that means, all the stresses are taken by the pile tip. Okay. So, this way we can determine how much load is transferred to the tip and how much load is taken by the friction of the pile. Now, I will calculate the settlement of a single pile by using this approach. So, now we know that how much load is transferred to the tip and how much is taken by the pile friction. Then now we can calculate what would be the settlement of pile. So, again for floating pile, that settlement rho is equal to P I by E s into D. So, P is the applied axial load then ES is the elastic modulus of the soil D is the diameter of the pile and I is equal to I 0 R k R h R nu. Okay. Now, what is I 0? This I 0 is equal to settlement factor for incompressible pile when mu s is equal to 0.5. Okay, so that means this is the settlement influence factor for incompressible pile. So, again for incompressible pile R k is 1, then for mu equal to 0.5 R nu will be 1 and R h is the another factor which is due to the finite depth of layer. So, previous floating pile we have assumed the depth of layer is infinite, but if the depth of layer is finite, suppose your floating pile is like this is the pile and there is a finite depth of the layer. It is floating pile, but this is the L and this is say h, small h, which is the thickness of the layer. Then also you have to apply the correction factor, because this I is for infinite depth of the or thickness of the layer. If it is a finite, then you have to apply the correction factor. So, these three correction factor, one is the compressibility of the pile, one is the Poisson ratio of the soil and another is the for finite thickness of the layer. So, again the R k is the correction factor for pile compressibility compressibility, R h is the correction factor for finite depth of the layer or finite thickness of the layer on a rigid base and R nu is the correction factor for Poisson ratio. Like this one, here also correction factor for these three cases, here also we have to apply the same correction factor. Okay. Now, for how we will calculate this correction factor. So, this is I 0 will get for different L by D and again for d b by b I 0 value, and if L by D is greater than or equal to 50, then I 0 will be equal to this value, but this is valid for d by b 1 to 3. Then correction factor, this is for R k chart for different L by D and the k value. Then this is for the R h chart, different h by L value, and this is for mu s Poisson ratio of the soil chart. This is for different Poisson ratio 0.5 to 1, 0.5 it is 1, different k value, and then we will get these correction factors for this chart or from this chart. Now, similarly for the end bearing pile, again the similar expression we can write pi I by E s d, where I is equal to I 0, R k, R b and R nu. So, R k R nu same as the R k R nu discuss about the floating pile, but here R h will not act here, because it is in this case it is resting on the ridge stratum itself. So, there is no question of R h, okay. But there R b is introduced, which will incorporate the effect of stiffness of the base soil where the pile is resting. So, that means here R b is correction factor for stiffness of the bearing strata. Bearing stratum. Okay. So, now how I can calculate the R b? So, this is the chart where I can calculate the R b. So, again for different L by D 75, 50, 25, 10 and 5, and for different E b by E s value and for different k we will get the R b value. Okay. So, these are the correction factor we will get. Now, this chart will give you that how we can calculate I 0 for different layer soil. If you have a layer soil for layer 1 and layer 2, the layer 1 thickness is H 1 and the layer total layer thickness is L. So, this will be L minus H 1. Then we will get for different E 1 and E 2, this way we can divide it by I 0. So, different E 1 by E 2 is the elastic modulus of the layer 1, E 2 is the elastic modulus of layer 2, and this 2, 5, 1, 0.2, 0.5, 1, 2, 5, we can get the value of I 0. Now, what is the difference between dotted line and the farm line? The farm line is the approximate computed solution, and the dotted line, if you take the average E value, and that means that if you take the weighted average E value, and then you follow the same process that we have done for the uniform soil, because here it is the layered soil and previous cases are uniform soil. So, in layered soil also you take the weighted average value and apply the concept of the uniform soil. Then also you will get more or less close result, but as the farm line is taking different E value, okay, into the analysis, not the weighted average. That is given the farm line, and the dotted line is for the solution for taking the average E value and using the concept of uniform soil. So, you use the farm line to determine the I 0 for layer soil. The 2 layer soil you have, and that is for H 1 is the thickness of the first layer, and that is H 1, and L is the total thickness of the first layer and the second layer, and D is the diameter of the pile. So, this is the pile which is on the ridge strata, then L is the total length of the pile, where E 2 is the your elastic modulus for the second layer, E 1 is the elastic modulus of the first layer. This way also you can determine the I 0 for layer soil. After that, the same way you have to apply the corrections as we are doing for the uniform soil. So, one option you use different E 1, E 2 value and then calculate the I 0. Another option you take the weighted average and use the I 0 value for using the uniform soil concept. So, if you do not have this chart for layered soil, you can use the average value and use the your uniform soil concept. Otherwise, you have this chart, you can use this chart for taking different E1 and E2 value, and then you will get the I0. So, next part is how I can use these analysis and how I can estimate the load settlement curve for pile to failure, up to the failure. So, this analysis is valid for L by D greater than 20. It is valid for L by D greater than 20 and load settlement is linear until 50 to 70% of the failure load. So, that means the load settlement behavior is linear up to 50 to 70% of the failure load. After that, it is non-linear. So, but actual load settlement behavior is non-linear, but here we will represent that load settlement curve by linear line or lines. Okay. So, let us see. The first I will discuss or determine that the shaft load versus settlement behavior. Versus settlement. So, as I discussed, the shaft load P s is how much? That is equal to P 1 minus beta, because beta is the amount portion of the load which is transferred to the tip. So, the shaft, the amount of load will be P into 1 minus beta, where P is the applied load Okay. So, because we have already discussed the settlement will be equal to P I by E s d, that is the settlement, or here in case of P I we are writing the P s because we want to determine the settlement due to the shaft load only. Okay. So, that will be the P s or detailed settlement due to shaft load. So, that will be P 1 minus beta into I by E s d. Now, how we can calculate the I that I have discussed, that you have to calculate I 0, and based on that you have to calculate the others factors, and then you have to multiply those factors depending upon your requirement, and you will get the finally the I value. So, now the second part is the base load versus settlement. Base load settlement. So, the base load P p or P b or P p, that is equal to beta into P. So, assume a linear relationship between the load and the settlement, we will get the settlement due to the base load will be equal to how much? I E s d and then P divided by B. P b by B, because here your okay. So, this way we can represent that. So, this is P b by B. So, this will be, I can write P so this line I have to slightly modify. Actually, this is the total load, and that we have to represent by P s. So, this will be P will be equal to P s divided by 1 minus beta. So, this is P, because the equation is given, the settlement is P I E S D. So, this P we are replacing with P s 1 minus beta. Okay. This P s we are replacing 1 minus beta. Similarly, here also this is P I E S D. So, that P we are replacing with P b. So, this will be I E S D, this will be P b divided by beta. Okay. So, that means we are using the actual equation, that is the settlement is equal to P I E S D. Now, this P is the total applied load. Now, this P has two parts, one is the P s, one is the P b. So, that means the P has two part, P s plus P b. Okay. So, now this P is replaced in terms of P s for in case of shaft, and in case of base the P is replaced in terms of P b. Okay. So, this is P is replaced by P s divided by 1 minus beta, and here P is replaced by P b by beta. Okay. So, in this way we can determine the what would be the settlement in terms of shaft load, and another the settlement in terms of the base load. So, in the next class, based on these equations, I will show you how we can determine the load settlement curve theoretically. Thank you.